Hi everyone, I'm Yansong, fifth year grad student here. So my topic today is about the dust physics inside the protoplanetary disk. So tiny formation takes place inside a disk of gas and dust, and we call it protoplanetary disk. And the entire process can be visualized as the coagulation of the submicrograins into larger and larger particles through collisions. And to understanding this process is challenging, mainly because the lack of observational constraint. We have the constraint on the last stage through the discovery of exoplanet, and we have the constraint on the very first stage through the observation of our protoplanetary disk. All the intermediate step is purely on theory, and which is heavily depend on the formation, heavily depend on the building blocks before that. So understanding the process at the first stage is very crucial to understand the whole process. So in this talk, I'm going to share how the ALMA observation of the protoplanetary disk review us about the formation of these small grains at first instance. So in 2018, there's ALMA survey released this stunning image, which shows a wealth of substructures there. And this image is observed in millimeter wavelength. So it's purely the dust emission at about 30 Kelvin. And but although these structures are very interesting, but keep in mind this in very large scale, about hundreds of AU. So they are not likely connected to the type of planet in our solar system. And with more and more observation data, we have a more complete sample of this. And we found actually most disks are complexes with about a few tens of AU in size. So much like our solar system. And but due to the limited resolution power, we cannot see the fine structure of that. There are still some measurement we can make, such as the size of this, the total flux of it, and also the spectral intensity. We have multi-wavelength observations. So here we collect a large sample of this and plot their size and luminosity. We classify them by different star forming regions because this in the same region shares similar ages typically. And I want you to focus on two regions, which is Lupus and Upper Scorpius. They are representative because Lupus is one of the youngest disks with only age of 1 to 3 millimeters. And the Upper Scorpius, in the other hand, is more than 5 millimeters old. For reference, the typical lifetime of the disk is about 10 millimeters. So this disk in its late stage of the life. And surprisingly, we found that both populations follow the same scaling distribution, which is the luminosity scale with R squared. So basically the surface density of this. I ask everyone to think about for a second. What does this scaling relation mean? Then anyone know the answer? Just shut up. So basically,
This must be repetition.
so basically, if the luminosity scale with a certain level, but not depend on the actual mass distribution. It just means that the entire disk is obviously here. And this object interpretation is further supported by the spectral index measure. Here we see, here we plot the spectral index against the luminosity of the disk, and we found that most of this just cluster around the spectral index of 2. So what does the spectral index of 2 is? Here's fourth SED of the disk. We get it from the low frequencies, low wavelength, sorry. And in the low wavelengths, we have star emission, and then the emission of the inner disk. And then when we further increase the wavelength with the outer disk here, and the ALMA is observing in one millimeter, so 1,000 micro here. So in this range, we only have the emission of the outer disk, and the outer disk has temperature around 30 Kelvin, which peaks at here. So we are actually in the really thin scale here. It means the intensity scale with frequency squared. So a spectral index of 2 just means that they are blackbody here. So basically from the observation, we can know, regardless of the age, the disk always have all this big emission. But this kind of observation that all disks are still packed with solid mass is in conflict with field. In fact, large particles struggle to stay in a gas disk because of radiation. And the physics of radiation is because the differential rotating speed of the gas and dust. So inside a smooth disk, because the density, both density and temperature decrease outward. So there's always pressure gradient force pointing against the gravity here. So gas moves in circadian speed. However, for dust, they do not feel the pressure. So depending on how coupled are they to the gas, they will feel a headwind from the gas. So their angular momentum is constantly losing. So they will move inward and finally fall into the star. On the right, it's a plot of the relative time scale against the green side. We can say for micrometer dust, because they are tightly coupled to the gas, so they feel very little radiation. And when they go to 1 meter in size, they become loosely coupled to the gas, so they feel the maximum drip rate. But when they go even larger, because they are just too massive, the air drag becomes irrelevant. So the radiation becomes inefficient again. So with this physics in mind, let's derive the radial drip efficiency inside the disk. First, we assume the grain growth is limited by the fragmentation barrier. And the relative velocity of the dust is determined by how coupled are they to the turbulent eddy of the gas. So we get the relative velocity, and that we equate this velocity to the fragmentation limit of gas. We take 1 meter per second here. It's determined by the lab experiment. So we find we reach the A max to be 1 centimeter here. So 1 centimeter grain loosely covered the gas. So when we calculate the radial drip speed of it, and then find the drip time scale, we find a very short time scale here, about 0.5 millimeters. We know this is wrong because we see those Upper Scorpius that is much older than this, but still have a lot of dust mass. So what is wrong? It seems like we oversimplify the dust collision of physics here. So when two grains collide, depending on its relative velocity, it can be the outcome can be classified into 3 categories. Just imagine if you apply the 2 ping pong balls that is made of sticky surface, then if the collision speed is very slow, they will stick. But if you apply it with high enough velocity, they will just strand here. And the fragmentation limit is about 1 meter per second, depending on the material strength. And but when you apply it with some intermediate speed, such that is high enough, not high enough to fragment them, but high enough to pull them apart, pull the contact surface apart. Then the 2 particles will cross over each other. This limit is about 0.2 centimeters per second. It's about 3 orders of magnitude jump here. But inside of this is how this range of velocity are all possible, depending on where you are in this and how comfortable are you to the turbulent stress. Also, this bouncing limit has a dependency on the particle size, because if you again imagine with the same stickiness, if you collide 2 basketballs, it's more likely to bounce off that when you collide 2 ping pong balls. Simply because they have more momentum here. So, and such physics is tested in lab experiments, in simulations, and it's well handled in theories. So when now we put the new bounding physics into the equation and derive the green growth again, and we found that the bounding physics effectively limits the green growth. Now the green only grows to about 100 micron here, and 100 micron green are like the 1 centimeter grains. They are highly coupled to the gas, so their drip time scale is very slow. It's 50 meters here. So now we are consistent with the observation here. This can be correct for many years. And to confirm this point, we simulate this evolution. So here's the radial profile and different simulation time. The left panel is the model with no bounding yet. So the green growth is limited by fragmentation. We see the green just go to a centimeter here and drip very fast. The surface actually of the gas, the dust just jump sharply here. And when we put in bouncing, the green growths are all limited at about 100 micron, and as we to predict, they bear the drip. So what's the observation consequence of the bouncing? Now we measure the size and luminosity of our model, and comparing with our observation, which is showing the contour here. And So each track here is model with different in the initial size. So all of these models are going to not fully bouncing. We see this just decrease in size and then decrease in luminosity very fast. Again, because of the radio tube. But with the bouncing, we see that this just stay on the line, which is of the big one. So we conclude that we have to include the bouncing in order to become consistent with the observation. So now we confirm that the disk is full of 100 micrograins, and they can stay there for millions of years. Then what happens next? How can they go to the planet? So the first thing we consider is the streaming instability, which is the leading theory in the planetesimal formation. So the streaming instability allows the centimeter petals to jump across the fragmentation barrier into the kilometer planetesimal. But we find that for 100 micrograin, the streaming instability unfortunately is not effective. So we have to think about another way. Currently, we don't know the answer, but some research has suggested that if the bounding is not perfect, but with some mass transfer between two grains, then some lucky seed might be able to go to the larger side and finally reach planetesimal. But more work needs to be done here. And I will just end my talk here with a slide of knowledge.
All right, let's start back again.
When you look, you said the fit was really good, and that's true for the luminosity versus radius, but your spectral slope was not quite right. I think, is that because your grains are basically a bit small, so you expect at the ALMA band to already see that in the spectral slope, that they're not efficient blackbody?
Yeah. This figure.
Yeah.
Yeah, good point here. Because the green goes, yes. So the dust of acid change a bit. So we see this thing, and also the spectral index is like we did by the flux. So it's very sensitive to the outermost part of this. So there's still some tricks there. So we cannot be sure it's perfectly optimistic here. But at least comparing to the no.
Yes, yeah, no, for sure, that was much better.
But to just add on that VLA observation of the same disk. So they are both, these are ALMA data, but they also VLA data, much longer wavelength. And they show that the same, there was being deep consistence being coming off with thin.
Okay.
The grains are pretty thin and therefore the answer is thin.
Thanks.
Hi, thank you. I have a question. So in this case, the level of stickiness is a constant parameter, right? So I was wondering, would you think of some kind of continuum where are the chemical or physical properties on the surfaces make certain conditions to be more sticky? That could lead to some fraction of the larger grains actually sticking, but not where most bounce with some stick.
So for example, like ice cream, they will be more sticky. And also this bound also depend on like the porosity of the grains and so on. So here, so I can see we do not have enough parameter space in the lab experiment. But I think this train here, like the velocity here in the first and depending on the wavelength here is confirmed in both the lab experiment and the numerical simulation and body simulation. So I think that the normalization will not off by too much depending on the speed. So I think of course this is just an estimate here. We need more experiment in the future. But it's just all magnitude estimate.
I think you should bring in demo.
Sticky phone call.
Give the talk in winter and bring snowballs.
Yeah.
Well, I was gonna ask, anybody ever saw snowball bouncing on each other?
We'll bring this.
What?
Don't break, yes.
They never bounce off each other, right? Because they're so weak. So you have to pack them really, really tight and then the two snowballs can bounce off each other. So this is the same physics.
But they're bigger than 100 microns, normally.
I'm usually going as faster than 1 meter per second.
And kind of a related question, on your last slide, you talked about getting sort of the mass transfer. Are experiments the best way to test that too, or do you think like, can you,
To test which.
well, to think about the mass transfer?
Oh, yeah.
Yeah,
Yes, of course, there is experiment about it.
yeah.
There's also like simulation about
Okay,
it.
so-
When it is put that not for example, put that 1 centimeter seed in and so surround it with 100 microns.
Okay.
And that there are some close, but of course we cannot like evolve it for so.
Yes.
I think you said that the oldest systems you observe are like 10 million.
Yeah, 5 to 11 meters.
Does that mean that there are none that are older and that they kind of form planetesimals very quickly at that point, or? Is there a reason you don't observe ones that are older than 11 million years?
The reason why the line lifetime is only 10 years.
So does that mean, because they're opaque, right, for those first 10 million years, does that mean that they're suddenly forming planetesimals very quickly?
Yeah, good question there. So I have the thing I haven't talked about is this frequency here. So in Lupus we have like about 70% of the stuff have this amount. But for Upper Scorpius, a lot of this have already disappeared. We only have about 30% of the stuff has this. So, but the strange thing is we do not see this that is disappearing. We only see the two extremes either way or it's the opposite thing here. So one proposal is about all the planet formation process can be very fast. That all with just collecting the planet and then it disappear. But yes, we still need more research for that.
As this is up, what was this thing with USCO Enter 2020 and then this work? And why is there such, that's presumably the same data, but why is there such a difference?
Well, so this dot here, the dot field here is the measurement of previous work, and they have they argue that for the oldest days they just become all object things because they are things similar. But we confirm that because now we have like the module wavelength data Yeah, and then we got confirmed that, their radio measurement is wrong, and it should be, should be. And also, just, few weeks ago, there's a new observation of this, and they have a higher resolution, and found that, yes, it's kind of consistent with the objective.
Excellent, let's thank both speakers again.